Hello, my name is Doun Lee. I'm from Kookmin University. I'm here for my presentation with initialization based on gradient similarity for versatile machine learning. So my presentation topic would be that the unlearning is only as private as its weakest property. So let's start by saying what is an unlearning and how unlearning is evaluated. So an unlearning is like a task of reverse of a learning. So its task is to forget specific data from a learned model. So unlearning is evaluated by first we have original model, which is trained by the train set. Also, train set is composed of the retain set. We wish to retain the information of it, and the forget set that we wish to forget. And unlearning starts by giving us the forget request of the forget set. So unlearning both uses the train set and the original model to produce the unlearned model. Also, we have the gold model, which is also called as exact unlearning or the retrained model. So the gold model is trained from scratch using only the retained set. So many of our learning evaluation algorithm compares the unlearned model to the gold model in multiple aspects. So in our research, we found out that method targeting specific model property can still leak information in other model property. So let's assume that we have an adaptive attacker. He will query the forget set sample, and he will observe the model output, and he will likely choose the model property that will reveal the most information out of it. So let's see the example of Salon in the right. So we have the original model, which has trained on the forget set, gold model, which hasn't trained on the forget set, and the Salon, which has trained on the forget set and tries to unlearn the forget set using Salon. So in the perspective of the original model, the probability of the true level of the forget set would be high because it was trained on the forget set, and the entropy would be low. For the gold model, the probability of the true level of forget set would be similar to the reference as test set, and the entropy would be similar to the reference, as the both forget and test sets are just two different held out data set in the perspective of the gold model. Also for the Saloon, so Saloon uses a random label based fine tuning as its core mechanism. So given forget set, it relabels the forget set using randomly chosen label and fine tunes the model using those relabeled forget set. So probability of the true level of the forget set would be low because it was to train to predict a different label already. However, the entropy is still low because it still minimizes the cross entropy loss. So for the loss and the true level probability, also called as confidence, would be close to the gold model, which is the exact thing that Saloon wanted. However, for the entropy, the output of the Saloon would still be distinguishable from the gold model, which is a privacy leakage. So targeted unlearning can reduce leakage in one property while leaving other property exposed. So we created an average gap to measure this. So we averaged the gap between the gold and the unlearned model by aggregating the membership inference attack from loss, entropy, and confidence, and the accuracy of the forget set. So lower average gap means that it's closer to the gold across more model property. Also, the membership inference attack, loss, entropy, and confidence are all driven from 3 different model papers that used to evaluate the learning. So this is figure 1A from a paper. So we counted the number of insufficient learning that ranked in bottom 30% of the given membership inference attack. So as you can see, Solon shows a good performance for the loss and confidence-based membership inference attack, but it shows some failure for the entropy-based membership inference attack, which is the supporting evidence of the demonstration we showed you in the slide 2. Also, interestingly, the confidence-based membership inference attack was the one that was used for the Saloon's research to evaluate their algorithm. Also, we have a Scrub. So Scrub uses a gradient ascent-based method, which directly uses loss for its learning. So if you see the result, it shows a good result for the loss. But however, it shows so bad result for the membership inference attack on entropy and the confidence. Also, interestingly, the loss-based membership inference attack was the one that was used to evaluate the Scrub's algorithm in their research. Also, the entropy-based membership inference attack was used for the bad teacher. So we hypothesized that current learning algorithm may have been overfitted to certain model property because they only have evaluated only one-sided model property membership inference attack, and they directly use some model property of the forget set as for their learning. Also, in our algorithm, our proposal weak shows no zero insufficient learning in this figure. So to handle this, we designed our algorithm weak to structurally approximate the exact unlearning. So exact unlearning can be seen as a 2 steps. First, the full initialization. Second, the full training using the retained set. So we approximate this by step. So the full initialization, we approximate by the partial initialization. And for the full training using the retained set, we approximate by the shorter fine tuning using the retained set. So because you only partially initialize the model, the partial of the information is still preserved. Therefore, even with the shorter fine-tuning, the utility can recover faster. However, the utility recovery is not the only purpose of this later fine-tuning, because it needs to also perform a catastrophic forgetting on the forget set. Because in otherwise, in many cases, the forget and the retain set have some like overlapping data distribution, and even if it doesn't, it can have some shared feature. So it needs to perform a catastrophic forgetting on the forget set. So in the partial initialize step, we need to like initialize the weight that will demagnify the catastrophic forgetting on the forget set, while preserving the weight that will likely magnify the catastrophic forgetting on the forget set. So to do this, we use the metric called OVL. So we collected the gradient statistic of the forget and the train set, and we created Gaussian distribution of it, and we measured the overlapping area of those two Gaussian distribution, and we selected the top K% weight that had the largest overlapping area, and we initialize those. So we try to indicate the shared pathway using gradient similarity, and we use the Gaussian as an efficient proxy for the top K weight selection. Yeah, so was one of our evaluation. So we measure the average gap as the training progresses. So if you see the plot, the all metric other than high OVL shows a high average gap, or shows some kind of uptrend in the as the training progresses, which means that the information of the forget set has been reoccurred as the training progresses, which is the exact problem that we wanted to avoid. So in other hand, high OVL shows a minimal and consistently lower average gap. So this is our experiment result using Cyber10 and ResNet. So in both random and class forgetting scenario, weak shows the smallest average gap, while showing the best test accuracy for the random forgetting scenario, and while showing some decreases in the class forgetting scenario. So which is like privacy utility trade-off in approximate learning. Also, we additionally have some experiments on multiple models like VGG and VAT and additional data sets such as ImageNet and SpeechN, and also another task including the image generation using stable diffusion and additional learning scenario like selective learning scenario which is included in our paper. As many of our personal learning algorithms do, we cannot really verify the sample level of removal. So it's important to show versatility in multiple learning evaluation algorithms. So we evaluated our algorithm in like 4 different learning evaluation algorithms. So we show the top performance for the interclass confusion test, ULIRA, and the machine learning challenge that was held on Kaggle, and it shows the best top 2 performance for the Gaussian Poisson. So today my presentation's point will be that the good online performance on one model property may not generalize to others. Also, to handle this, we proposed a weight initialization based on gradient similarity. For characteristics doublets weak, it proposed which does a weight partial initialization based on gradient similarity, followed by the retained set fine-tuning. So if you have any questions, please visit my poster for more detail and discussion. Thanks for listening to my presentation.